Thank you. Yeah, this is 5 years of cloud-native Rust. So my name is Alex Leong. I am one of the maintainers of a project called Linkerd. Has anybody heard of Linkerd? Is that name familiar to anyone? Maybe just a few people? Okay, cool. So Linkerd is a service mesh. It's an open source project. So it's a service mesh for Kubernetes. And I'll talk a little bit more later about exactly what that means. It's a graduated project of the Cloud Native Computing Foundation. And we made this big decision about 5 years ago to adopt Rust as the programming language that we would write Linkerd in. And so this talk is basically about that journey and why we made that decision and kind of what the outcomes of that have been. So I'm going to talk about why, a little bit closer, yeah. I'm going to talk about why we decided to use Rust in Linkerd, kind of what went into that decision and how we decided that that was kind of what we needed to do and why we made that bet. And I'm going to talk about how that went and kind of what the outcomes of that were for that project. And then I want to talk a little bit about what that means for the ecosystem, for the greater ecosystem, and whether that means that Rust should be adopted more broadly. So number one, why did we choose to use Rust? Well, before we can even answer that, what even is Linkerd? So Linkerd is a service mesh. And so what that means is that we run a small sidecar proxy alongside every instance of your application. And all of your application's traffic is redirected, so it goes through that proxy. So all the traffic going in to your application first goes through the proxy, and all of the traffic going from your application out goes through the proxy. And what that means is that proxy, since it's intelligent and it's aware of level 4 and level 7, it's able to do a lot of really cool things with that traffic. Like it's able to add mutually authenticated TLS automatically on all those connections. It's able to detect things like success rate, latency, and request rate and emit those as metrics that you can consume in Prometheus. It can use those latency data that it observed to do intelligent request load balancing, so it can load balance HTTP requests and weight that by the latency, so you get more traffic going to the faster replicas and less traffic going to the slower replicas. And all kinds of other really, really cool stuff. Circuit breakers, observability, reliability, retries, timeouts, all kinds of stuff. It's super cool. But kind of the consequence of this architecture is that all of your application's traffic is flowing through this proxy. In fact, because your application probably is made up of multiple services, the traffic is going through that proxy, or those proxies, multiple times, one at each hop, or two at each hop if you consider the traffic going in and then coming out. So Linkerd is infrastructure, and there's kind of two different things that I mean by this. Number one, Linkerd is infrastructure for your application. It's network infrastructure. Whenever your application is going to make a HTTP call or a TCP connection or any kind of network call, it uses Linkerd under the hood kind of transparently, and Linkerd is responsible for getting those packets where they need to go. So just like your operating system is infrastructure or your network card is infrastructure, Linkerd is infrastructure to your application. But Linkerd is also used by infrastructure for humans. So for example, 911 call centers use Linkerd. Healthcare organizations and financial institutions all use Linkerd as part of their applications. And these are very critical services. These are things that people rely on. These are not things that, you know, if they work, that's great. If they don't, who cares? These are like things that cannot fail. And so infrastructure needs to be secure, reliable, and fast, in that order. And it's not negotiable. You can't compromise on any of these. So when we talk about these things being secure, well, what do we mean? What are we protecting against? What types of things cause security vulnerabilities? So one example of something that can cause a security vulnerability is a buffer underrun, right? You can be trying to access a piece of memory outside the legal bounds for that memory and access, you know, some invalid memory and cause a buffer underrun, buffer overrun. You can have an issue with dangling pointers or use after free. So trying to use a pointer after that pointer is no longer valid, either because the data that pointer has pointed to has moved or has been deleted, or for whatever reason that pointer is no longer valid, but you try to use it anyway. Or kind of the flip side of that, reading uninitialized memory, so reading a piece of memory before it's valid. So these are all different examples of what we call memory unsafety. Basically accessing a piece of memory, assuming that it's one thing when it's actually something else. And it turns out that these memory unsafety issues are responsible for a surprising majority of security vulnerabilities. 90% of Android vulnerabilities are caused by memory unsafety issues, 60 to 70% of iOS and macOS CVEs, 70% of CVEs in Chromium, all due to memory unsafety in one form or another. So one way to get around this is to use a managed language, right? You can use Scala, you can use Java, Go, C#, Ruby, Python, any language that has kind of this runtime that checks these memory safety things as the program's running at runtime, and do things like bounds checking and making sure that the memory you're accessing is valid. But doing those kinds of memory safety checks at runtime have a performance cost, right? There's always some overhead associated with that runtime. So on the other hand, there's languages like C and C++, which are very fast. You know, you don't have this overhead from doing those runtime checks to make sure that the memory you're accessing is valid, but they're also unsafe. They're vulnerable to these types of issues. So when we were thinking about what we needed to do for Linkerde's data plane, and when I say data plane, I'm talking about those proxies which all the data in your application is flowing through. We decided memory safety is unacceptable. There's too large of a class of security issues that are caused by memory safety issues that we didn't want to be susceptible to. But on the other hand, using a managed language, like for example something that was built on the JVM, means you're susceptible to things like garbage collection pauses or other pieces of overhead caused by the runtime. You know, when you're handling traffic for a critical application like a 911 call center, you don't want to have a request paused because your application is going through GC, right? That's not really acceptable. So we thought, well, what if there was something else that we could use here that would give us kind of the best of both worlds? Something where we could get both memory safety, but also kind of these fast speeds that you get from a language like C or C++. So that's where Rust comes in. So Rust is a systems programming language, and it's very cool because it ensures memory safety at compile time. The Rust compiler does all of these checks when the program is compiled to make sure and to guarantee that the coded outputs will not perform any illegal memory operations. And because of that, you don't need to do these checks at runtime anymore because they're statically guaranteed. So how does Rust do this? How does this work? How does Rust help us write safe code? So one idea in Rust is that there is this idea of unique ownership, which means that any piece of data in your program is owned by exactly one piece of code. And so you don't have two different pieces of code which are both trying to access the same data, both thinking they own it, both trying to manage it, and kind of leading to issues where maybe one deletes it while the other's accessing it or something like that. If you want to access a piece of data in your program that you don't own, there's this concept of checked borrows, where you can kind of borrow it, but there are a lot of rules in place to make sure that if you're borrowing data, it's not going to change out from under you. And this is kind of accomplished with this idea of exclusive mutability, which is that if you want to change a piece of data in Rust, you need to kind of be the sole person or the sole piece of code that has access to that data at that time. So you're never going to change data out from someone else while they're reading it. So let's look at some code examples, because this is a little bit abstract. So this is a C++ program. It is pretty simple. So we start out by creating a vector of strings called v. So that's a growable array. We're going to push a string into that vector called hello world. We're going to create a pointer to the first element in that vector called ptr. Then we're going to print out the contents of that pointer, or what that pointer references. So hopefully that's hello world. Then we're going to push a whole bunch of other strings into there. And then finally, we're going to print out that first pointer again. So that should print hello world again. So we would expect, if this program were correct, it would just print hello world twice. So if we try to run it, though, it doesn't do that. It prints hello world once and then seg faults. So what happened? Like, this is such a simple program. What could have gone wrong? Well, it turns out that V, remember I said is a vector, is a growable array. And the way that works is that it's backed by a fixed length array somewhere in memory. And so we create a pointer to that first element of that fixed length array, and then we add a bunch of things to the vector, and that causes it to grow. And if it exceeds its capacity in that fixed length array, it needs to create a new array somewhere else in memory that's larger and move all of its contents over to that new array. And when it does that, our pointer to that first element of that vector is no longer valid. We're now pointing to where that vector used to be. And so that causes the segmentation fault. So we're accessing a pointer that is no longer valid because it has changed out from under us without our knowledge. It's pretty sneaky. So let's see how Rust can help us here. So this is the same program written in Rust. So this should look pretty much identical. We've got a vector called v. We push a string into it, hello world. We take a pointer, which points to the first element of that vector. We print it out. We push a whole bunch more strings into it, and then we print it out again. Right? So basically the exact same program. Does anyone have any predictions? Do you think this is going to work when I run it? Think it's not going to work? It's not even going to compile. We get a compiler error. So this is really cool. So what does this compiler error tell us? It says cannot borrow v as mutable because it's also borrowed as immutable. And so what that means is that we have this pointer to this vector, and while that pointer is still valid, while that reference is outstanding, we tried to edit v. We tried to mutate it. And that is not allowed. That violates exclusive mutability. And so the Rust compiler is able to tell us, hey, this is going to be a problem. You can't do this. This violates the rules of exclusive mutability. So how do we fix it? Well, it's pretty simple. If we just recreate that pointer down at the end, the compiler is smart enough to know that that first instance of the pointer is short-lived. It only lives as long as that first print line, and then it's never used again. So they can be discarded at that point. And then once we try to do the v.pushes, that mutation, it's allowed because we don't have any outstanding references to v. No one else is looking at that data, so it's safe to mutate. Then once those mutations are complete, we can recreate that pointer and everything should work. Ta-da, hello world twice. Pretty sneaky. Let's try another one. Okay, so here's another C++ program. We have a class called greeter that contains a reference to a string called who. There's a constructor for it, and then there's a greet function which prints out hello and then whatever that who string references. We have a function called makeHelloWorld, which creates a string called world and then passes a reference to that string into a greeter and returns it. And we have a main method that calls makeHelloWorld and then calls greeter.greet. There's a bug in this program too. This one's maybe a little bit easier to see, but let's try running it and see what happens. Whoops. There we go. So it does print hello, but it doesn't print hello world. It prints hello and then a whole bunch of nonsense. So why did this happen? Well, it's a little bit similar to the previous one. When we create that string world in the makeHelloWorld function, that is a stack local variable. And so we return we take a pointer, a reference to that local variable, pass it into greeter, and then we return. And when we return from that makeHelloWorld function, all of those stack local variables go away. But that pointer to that stack local variable kind of escapes that scope because we've given it to the greeter and returned it. And so now we have this reference that is no longer valid. It's a reference that has outlived the lifetime of the data that it references. And so when we try to print it out, we're pointing to who knows what, and we get a whole bunch of garbage. So again, we can kind of rewrite this program in Rust and see how is that different. So this is the same program in Rust. We have a struct called greeter. It holds a reference to a string called who. We have a greet function which prints hello and then the contents of who. And then we have a makeHelloWorld function which creates a string called world, passes it into greeter, and then we have a main method that calls makeHelloWorld and greeter.greet. So again, we can try to run this and see if Rust gives us any more protections against these types of bugs. And we get a compiler error again. So this is great. This is the Rust compiler protecting us, telling us that these types of things are invalid. And so what is this error? This says missing lifetime specifier, expected named lifetime parameter. And so what this is saying is that in Rust, there's this concept of reference lifetimes, where a reference might be only valid for a certain amount of time. And it's telling us here we need to annotate these, this code to talk about those lifetimes, to say, hey, this is a reference, but it's not just any reference, it's a reference that's going to live from here to here. And if you try to access it outside that valid lifetime, that's not going to work. The other cool thing here is that not only does the compiler tell us that there's an error, but it also gives us a suggestion about how to fix it. So you can see there it says, try adding these TiKV lifetime indicators, and that's kind of what you need to do. So we can just do what the compiler is suggesting here and add those lifetime indicators to our program. And now we've kind of got things parameterized on A, which is to say when we talk about a greeter, we're not just talking about any greeter, we're talking about a greeter that holds a reference whose lifetime is blah. And if we try to run this, it's actually just going to work. And the reason for that is that the compiler is able to determine that that world string is just a static string. It's not created dynamically, so it can be allocated statically, and therefore its lifetime is the entire lifetime of the program. And so it's able to kind of infer that all of those lifetimes are going to work out. You're always going to access those, that reference at a time that's valid for it, and everything's great. So this is a little bit of a trivial example because the lifetime in question is just the static lifetime, which lives for the whole program. But there's definitely a lot more sophisticated things you can do with lifetimes that only live for certain amounts of time. And the Rust compiler will check you at every step of the way to make sure you're not doing anything invalid. So those are kind of the reasons why we adopted Rust for Linkerd. That's what motivated it for us. We wanted to avoid these memory safety issues. We wanted to have confidence that we were kind of free of this category of bug. And we also wanted that kind of blazing fast performance. And so we had these design principles when we were starting out with Linkerd, specifically Linkerd 2, which was the rewrite in Rust. So the principles were keep it simple, minimize resource requirements, and have it just work out of the box. And I want to especially talk about number 2, minimize resource requirements. Because with a language like Rust, it's very easy to minimize memory allocations because you're very aware of every time you allocate memory. You're very aware of how memory is created and shared. That's kind of always at the forefront when you're writing a program in Rust. So it's very easy to keep that in mind and not have memory kind of run away from you and allocate a bunch of stuff unintentionally. So in Linkerd 2, we were definitely able to minimize memory. And similarly CPU, because we didn't have that runtime overhead. But we're also thinking a lot about resources like latency. If your application has a latency budget of 100 milliseconds before it starts to feel slow, if your proxy at every step is eating a significant portion of that latency budget, that's not good. And so latency is kind of a resource too that we wanted to make sure that the proxy was fast, not just efficient, but also fast. And the other type of resource is human resources. If you need a whole team of people to manage this piece of software, that's very expensive in terms of engineers or operations people or just human resources that are very expensive. And similarly, if you have a security team that has to fight fires and respond to vulnerabilities all the time, that's also very expensive. So security and operability were huge things of huge importance. Now Linkerd is actually made of 2 different pieces. I've been talking a lot about the data plane, which is the proxy, where all the traffic is flowing through. There's also the control plane, which is a piece that sits separately to that and controls those proxies. So it pushes configuration to them, it reads metrics from them, it gives them things like TLS certificates and manages revocation and rotation. And so the control plane and the data plane have very different requirements. Because the data plane is proxying all that traffic, that's the hot path, those need to be secure, fast, and efficient, right? No compromises allowed there. And because of this, Rust was kind of the only choice for us. It was the only language that really gave us the best of both worlds in terms of speed and safety. But when we were making this decision back in 2018, the state of Rust was not as mature as it is today. So for example, there were no production-ready HTTP2 or gRPC implementations at that time. So we helped to build them. It's Hyper H2 and Hypertonic. And async Rust, just in general, was still in its infancy. So we invested a lot in a lot of the different projects in that ecosystem to kind of help get it off the ground. So for example, we invested a lot in Tokyo, which is Rust's async runtime for doing async I/O. Like I said, we've invested a lot in Hyper, the HTTP and HTTP2 implementation. And in a project called Tracing, which is an async-aware logging library that was created for Linkerd, but has since been adopted kind of widely throughout the ecosystem. And this choice for us to adopt Linkerd, or for Linkerd to adopt Rust, has really paid off. So this is a latency comparison between Linkerd and another service mesh called Istio, which uses a different proxy called Envoy. And you can see that the latencies here in Linkerd are just, they stay nice and low and fairly close to the baseline of just having the application by itself. It's kind of paid dividends in resource efficiency, so that's the same comparison again, but in terms of CPU usage and memory consumption, you can see that Linkerd is just using a tiny fraction of the resources. And maybe most importantly, it's paid dividends in security. So this is Envoy, the proxy, the other proxy that I was talking about, written in C++. And you can see that the majority of these vulnerabilities are in that column there, memory corruption. So these are exactly the issues that Rust protects us against. These are exactly the things that we don't need to worry about because Rust guarantees that these types of things won't happen. So this is all for the data plane, the proxies. But what about the control plane? The control plane is not actually in the application's data path. You know, it's just pushing down configuration and managing these proxies. So if a piece of configuration takes, 100 milliseconds longer to propagate, it's maybe not the end of the world. So because it doesn't have that latency requirement that the data plane does, we have a little bit more freedom in our choice of language here. Rust isn't maybe as necessary. So a managed language like Go is actually a great choice, and that's what we decided to do. We used Go for the control plane and the CLI because this let us very easily integrate with the rest of the Kubernetes ecosystem, which is very Go heavy. And we were able to get access to a lot of good libraries for interacting with the Kubernetes API, which is what the control plane primarily does. But with that said, in 2022, we introduced a new policy controller into the control plane, and we wanted to see what it would be like to write a piece of the control plane in Rust. So in order to do this, we used a library called kube-rs, which is for interacting with the Kubernetes API. It's a Rust library. It's kind of the equivalent of client Go from Go. And we did it. It worked pretty well, but there were a few things that were still a little bit difficult. Especially around writing controllers in Rust. There's a lot of stuff in client Go around watching resources for state changes in Kubernetes and doing reconciliation loops that just kind of wasn't, there wasn't a lot of infrastructure in place for that. So we wrote some. We created a library called kube-rs, which is a batteries included runtime for writing controllers using kube-rs, and it kind of handled all of those shortcomings that I was talking about in terms of what you need in order to write a controller for Kubernetes in Rust. So if that's something you want to do, check out that library for sure. Okay, so why does this matter to you? Well, I think if you're doing anything with financial data, health data, any sensitive data whatsoever, you really owe it to your users to avoid these security vulnerabilities that you're susceptible to if you're using a memory unsafe language. And if you also can't afford the runtime overhead of a managed runtime, Rust may be one of your best options. So if that sounds like you, if those sounds like your requirements, try Rust, give it a go. It's pretty cool. This is a quote from Alejandro, who's another one of the Linkerd maintainers who didn't have any Rust experience prior to working with it on Linkerd. And he says, "It doesn't cease to amaze me that when something finally compiles in Rust, there's a high chance the program will simply work as intended." Which is kind of the best thing you can say about a compiled language. So we believe that the future of the cloud will be built in Rust. future of Linkerd certainly will be. Thank you very much.